Can everybody hear me? It sounds pretty loud. Let's turn it down a bit. Can you still hear me okay in the back? Yes. Too loud or good? Okay. Okay, let's get going. Okay, so how's milestone 3 going? Is it going well? Is it going poorly? If it's going well, put your hand up. Okay, it's going well for at least one person. If it's going poorly, put your hand up. Okay, nobody is going poorly, maybe one. Okay, and everybody else is somewhere in the middle. Okay, hopefully it goes well. Okay, so we're done talking about milestone 3, unless you guys have any questions about it, and we're on to milestone 4, which is the last milestone you guys have to do. It will build on top of some of what you've done for milestone 3. So, any questions about milestone 3? Okay, and if not, okay, we'll go on to milestone 4. I can see you're hungry for it. Milestone 3 is old news. Let's go on to the next thing. Okay, so milestone 4 is a courier company delivery optimization. Okay, so what do I mean by that? So the definition of the problem is you're first given several truck depots. So several spots where you can go pick up a truck, and you got to go drop the truck off wherever you picked it up at, okay? But you get to pick which one of these depots you want to go to. You then have a whole bunch of deliveries to make, okay? So I've shown them here with up arrows and down arrows. So we've got to pick up a package, A, and we've got to drop it off somewhere else in the city. And then we've got to pick up a package B, we've got to drop it off somewhere else in the city, and so on for package C and for package D. Okay, so in this particular problem I've given you, we have 4 deliveries to make. So I'm going to call that N in some of the slides that I show you. Okay, so we've got N deliveries to make. We have D depots that we can choose to get our truck from and to return our truck to. Okay, so in this case, D equals 3. And all of these things are intersection IDs. So I'm going to give you your deliveries are basically a pair of intersection IDs. Go to this intersection to pick up a package, go to this intersection to drop it off, and your depots are also intersection IDs. Go to this intersection and you could grab a truck. Okay, so what are you trying to do? You are trying to find a low travel time path that completes all of these deliveries. So you have to start and end at one depot, but you get to pick. So in the problem I've shown you here, there are 3 different places you could go to get a truck. You pick which one you want to use. If you get it from a depot, you return to the same one. You have to make all N of these deliveries. And the way you make a delivery is you just traverse the intersection. So we're considering you to be a very fast delivery driver, right? You get to that intersection, you just dash out of the car, drop it off at the location. You don't have to pay any time for that. In order to make a delivery, you have to pick the package up before you deliver it. So if I want to make delivery D, I have to go to this intersection sometime before I go to this intersection, right? So that I have the package and then I can drop it off when I go to the drop-off location. Okay, and what you're going to, you also have to tell us the path you follow between these intersections. Okay, so if I pick up my truck at depot 1, and then I decide the first thing I'm going to do is I'm going to go pick up package D, part of your solution is going to be, well, how did I get there? Okay, so you're going to build on your milestone 3 solution to actually say, well, here's a path. Here's a bunch of street segments that I'm going to follow to go from depot 1 to pick up the package D. And that's not going to be all that I have to tell you. You know, maybe you might say, okay, well then I'm going to go drop it off at this other intersection where package D is supposed to go to. You'll have to tell me all the street segments you follow to get there. So it's basically a more complicated travel route that doesn't just go between 2 intersections. It goes through a whole bunch of intersections in an order that you choose so that you make all of these deliveries and you try to make them with the least travel time you can. Okay, and problems like this are real problems, right? This is an optimization problem that logistics companies actually use when they're scheduling trucks, trains, Uber drivers, etc. So there are all sorts of variations on this delivery problem of how do I do this efficiently. Okay, so possible solution. So let's say this is my solution that I give you. I start off at this depot, pick that one. I follow a path, so I go to the intersection where I'm supposed to drop off package B. Then I go to the intersection where I'm supposed to drop off package or pick up package D. Then I go over here, okay, and I drop off package A, and so on. So I go through all these intersections, and at the very end, I pick up package A at the end, and then I come down here and drop my truck off again at this depot. So let me erase my squiggles. Is this a legal delivery order? Would this actually satisfy the spec that I gave you? So you got two things to do. You need to give me something that's legal, that actually satisfies the specification. And then after it's legal, we would like it to be good, meaning that it has a low travel time, because there are many possible legal solutions to this. But let's just start with legal. So I started at this depot. I followed some set of street segments to get here where I can drop off package B. Followed another set of street segments to get here where I dropped off or picked up package D. Followed another set of street segments to get here and drop off package A, and so on. And this keeps going. Is this a legal solution according to the spec that I gave you? What do you think? Okay, so I started at a depot. I said that was one of the things I had to do, so that looks good. I went to this intersection where I'm dropping off package B. Can I drop off package B? No, I don't have package B, okay? So I'm a really bad delivery person. I came to this person's door, I just rang the doorbell, I have no package, it's embarrassing, it's awkward, right? Not a good delivery order. So this is a bad solution, it's not even legal, okay? So it's not enough to just go through all these intersections that I gave you, or we give you in some order. You have to go through them in an order that will actually result in making all the deliveries. So you've picked up packages before you drop them off. It's fine to go through the same intersection multiple times, we don't care. But you do have to make sure, like I never went back to this intersection where I was supposed to drop off package B, and I didn't pick up package B until much later. So I clearly didn't make that delivery. So I have some ordering constraints that I have to respect. Is everybody with me? And at the very end, I said I have to go back to the same depot I started at, and I did do that. Okay, so other than the fact that I kind of misordered my pickups and drop-offs, this was legal. Okay, so I need to make this legal. Here's an actual legal solution. So I've decided to start at depot 1. I follow some path, I pick up package D. I follow another path along the streets, I drop off package D. Follow along here, pick up package B, pick up package C. Go way over here, drop off package C. Go down here, pick up package A. Go way over here, drop off package B. Up here, drop off package A. And finally, I drop off my truck at the same depot I started at. Okay, so that was legal. I picked up every package before I actually dropped it off. I don't have to pick up all the packages before I started dropping them off, so I picked up package D and then I dropped it off right away because I was near the drop-off location. But I always had picked up a package before I went to the drop-off. So that's a legal solution. The output is in a header file that I'm going to release today. But basically your output is going to be a vector of what we call courier subpaths. Courier subpaths are basically kind of like a sequence, a vector of your M3 solutions. In M3, you give us a vector of street segments that go between two intersections. Okay, we're giving you a bigger pathfinding problem now. So you're going to give us a vector, and every element of that vector is going to say, well, there's a start intersection, there's an end intersection, and there is a vector of street segments that connect them. Okay, so you're going to give us like a bunch of M3 solutions that together make up this whole travel path. And if I followed along that path, I would make all these deliveries. The exact data structure you're going to see in the header file. It's not very complicated. Okay, so maybe I'll pause there for a second. Everybody understand the basic specification? Okay, sounds good. Okay, so it's always a good idea to get something going quickly. So we emphasize agile development in this course, and it's emphasized in industry as well. So it means get something going and improve it. So a simple solution we could use is as soon as you're done milestone 3, you can reuse your pathfinding code that knows how to go between two intersections to solve this problem. Okay, so a very simple algorithm I can think of is, I'm going to call find path the algorithm that I wrote for milestone 3. And basically I could say, well, you gave me some number of depots. We give them to you in a vector. Okay, so in the examples I was showing you, we gave you 3 depots that you could start from. I'm just going to ignore 2 of them. I don't care how many depots you give me. I'm going to start at depot 0. Okay, so I'm always starting there. So, and my find path algorithm takes 2 intersections. So I'm going to say start at depot 0, and I can't drop off packages before I pick them up. So I'm just going to go to the first pickup. I don't care if it's close or far, I'm just going to whatever was, we give you a vector of pickups and drop-offs as well. So I'm going to just go to the first delivery and whatever intersection I'm supposed to pick it up at. And this basically, I've called my find path routine. So I've got a vector of street segments that now get me from that first depot to my first pickup. And then I'm just going to do the deliveries in the order that they were given to me in the input. So we gave you n deliveries. I'm just going to make the deliveries in that order. So I'm going to say, okay, I picked up the package from delivery 0. I'm basically going to say, well, tell me how to get from that pickup location to the corresponding drop-off location. And that's just another call to this find path. Okay, so I want to go between these 2 intersections, tell me the street segments to get there, and I'm going to add that into my overall solution. So I'll just say, this is kind of pseudocode, I'll say just add that into my solution. So this basically made a drop-off, right? I went from my pickup location to my drop-off location. Now I need to go pick up the next package, so I'll say, okay, I'm currently at this intersection. I'm at the drop-off for delivery I. I just want to go to the pickup location for the next package, okay, I+1. So add that into my solution. And just keep doing that until I've actually picked up, well, I've made all my drop-offs except 1, and I picked up the last package. I just need to drop off the last package, so I'll make a final call to my find path, go from the last pickup to the last drop-off. And now I need to return my truck. I picked it up from depot 0 up here, so I want to go from my last drop-off to depot 0. So I just call find path over and over again. I didn't actually do any real optimization here. Whatever order you gave me the deliveries in, that's the order I'm going to make them. So everybody understand this simple algorithm? So if you have M3 working, you can get this going really fast. Okay, so what would this do on this problem? Okay, so I said I've got 3 depots, but I ignore 2 of them. I'm just going to always start at depot 0. And I'm going to go to the first pickup. Okay, so I used letters here, but my first pickup is going to be there. So the first thing I'm going to do is go from depot 0 to that pickup. And I call find path, and it tells me take the 401 and go there. Next thing I do is I say, okay, well, where's the drop off for that? And it's way back over here. So I'll call find path, and it'll tell me drive back on the 401 and go drop it off. Okay, now I've got to pick up my second package. It's there. It's called find path. I get to it. Need to drop it off. It's way down here. Okay, so call find path again. Next package to pick up is C. So I'm going to go pick that one up, drop it off. It goes way over across the city over to here. Okay, let me erase some of those, and so on, right? I've got package D, so I go back and get it, and I've got to drop it off up here. And then I have to go back to the same depot I started at. So the depot I started at was here, so I got to go back there. So that is my delivery route. What do you think of my delivery route? Is it very good? If you had an Uber driver, and you had to go pick up a bunch of friends or packages, right? So you give the Uber driver a list of tasks to do, and this is the way that he or she did it. What do you think? Would you give this person like a 15 or 20% tip and a 5-star rating? Yeah, this is like a terrible travel path. So this is a good way to get going. You can get this going. It shows you understand the spec. You've hooked everything together. But it's not very optimized at all, right? We kind of have an obsession with driving back and forth on the freeway. We're driving back and forth over and over again, going past things that we could do. So without thinking about the order, we won't get a very good solution. Okay, so a more logical solution, let's say I just decide I'll start off in this depot, and I go pick up a package, and I'm really close to I'm really close to the package 4, so I pick it up, and I can drop it off right away. And then I'm pretty close to another package to pick up, and another one, and now I go pretty far away, drop off a package, and on my way back I pick one up, and I drop off my last 2 packages and go back to my starting depot. So just by choosing my order more intelligently, this looks a lot less busy than the other one. There's a lot less travel here because I'm trying to go from where I am, I'm trying to go to something nearby. Okay, so you want to optimize the delivery order. Okay, so the first thing we should check is, well, could we just do this perfectly? Right? Maybe we can get a perfect answer. In milestone 3, we're actually getting you, at least when turn penalty is 0, to get perfect answers. So maybe we can do a perfect answer here. This particular problem is a variation on what's called the traveling salesman problem. And the traveling salesman problem is hard, okay? It turns out that you can't build up perfect solutions from smaller solutions. Now in Dijkstra's algorithm, which you're using for milestone 3, the reason it works so nicely is that you can actually build up bigger solutions that are perfect from sub-solutions that are perfect. That's basically that wave expansion. We're actually finding the best travel path to every node within say 1 minute of travel time. And from that, we can actually use that to build up the perfect travel path to everything within 1.5 minutes of travel time and so on. Traveling salesman does not have that property where you can build perfect bigger solutions if you have perfect smaller solutions. That makes it fundamentally harder to get a perfect answer. So there isn't any algorithm that can guarantee the best answer to this problem. But maybe we can just try all the solutions, right? We can just try everything. So let's see how big that is. Maybe it's fine, because we can write code, we can maybe use recursion, and we could try them all. So we're going to try all possible delivery orders. And we'll write a function that can evaluate the travel time given a certain delivery order, and then we'll just pick the lowest one. Okay, so how many combinations do we have? Okay, so we have D of these truck depots. So we can choose to start and end at one of D spots. So that's D choices. We have N deliveries to make. So that means we have, in terms of places we have to go two times N places. We have N pickups, N drop-offs. Okay, so how many ways could we visit that? Let's see if I have this on. Okay, so we have to pick one of D starting locations. So that's just D choices. That's not too bad. After we've picked a depot, how many choices do we have of what to do next? Okay, so we can go make any pickup. How many choices is that? This is not too hard, right? So if you have, I'm going to pause to make sure people are following me. How many different things could I do? How many choices do I have after I picked up my truck? And I got to go make my first delivery. So I'm going to go to E09. How many choices do I have? Sorry, say it again?
Yeah, the prior number of choices minus 1.
So you have prior number of choices minus 1. Yeah, so the very first one after, okay, so I pick up my truck, D choices, and now I'm gonna go pick up, I gotta go pick up a package, and I have N choices for that, right? So I can pick any one of those. Now, to simplify the math, I'm gonna ignore the fact that I shouldn't go do a drop-off yet, okay? I'm just gonna say, how many things could I do if I don't consider that some of them are illegal? Well, I could go to one of two N places. And now I think you're saying, then the next thing I could do is I choose, what do I do after that? So I went to one of these intersections, did a pickup or a drop off. Really only made sense to do a pickup, but let's say I just coded it to try everything and check legality afterwards. you've said, well, after that, you've got 2 n-1 choices, right? One thing is done, so that's right. So then I can go to 2 n-1 for the next intersection, and then 2 n-2, and so on. So I keep repeating that until I get to, the last thing, right? Which will last pickup or last drop off. To be legal, it'll have to be a drop off, but again, let's ignore that. So, and then I have to drop the truck off at the starting depot. That's just one choice. Okay, so how many choices is this? Well, D choices for where I start, and then 2 times n choices of go to one of these delivery intersections, then 2 times n-1 to go to one of the remaining ones, and so on. So this is D times 2n factorial. Now, a bunch of them are illegal because I didn't consider that, well, this 2n, all the things that weren't a pickup were illegal. But I'll just write code to check, and it makes my math a bit easier to do it this way. The answer wouldn't be very different if I tried to only consider legal things at every step. So some of them are illegal, but let's say we just check after. Okay, so this is how many combinations we have to check of are you legal, and then what's your travel time. So let's see if we could just write some pretty fast code to check this, and we'll just call it with all the possible combinations. Okay, so we're going to give you problems. Actually, we'll give you problems that are actually somewhat bigger than this, but at least 10 depots and at least 100 deliveries to make. Actually, our biggest ones are more like 200 deliveries to make. So if I plug in, well, how many combinations is that? It's 10 times 200 factorial, which is actually, if you type this in a calculator, it can't do it. So I had to go into Windows Calculator, which can do really big numbers to get what is the answer to this. So it's about 10 to the 377, which is a pretty big number. But computers are pretty fast. So what do you think? Is this going to be okay? Because you just try all combinations. So I'm going to go back to E09. So E09, what do you think?
I think it's too much.
Okay, so you think it's too big? Yes, computers are fast, but they are not that fast. Okay, so I'm going to, also, what I'm going to do to evaluate each of these, I have my milestone 3 pathfinding algorithm. So I'm going to invoke my pathfinding algorithm basically to connect all these intersections together. I've got like 2n plus 1 paths to connect up in each of these solutions. So I'm just going to call my find path to hook them up, and that's how I'm going to get the travel time. In milestone 3, making your find path take about 1/10 of a second for a typical problem would be quite good. So if I assume that I got a pretty good find path algorithm and I multiply all this out, I get something like 1 times 10 to the 378 seconds. Okay, so computers are not fast enough to do this. This algorithm is not looking good. So that is 10 to the 370th years. The lifetime of the Earth is about 14, or lifetime of the universe is about 14 times 10 to the 9th years. Okay, so this is like vastly bigger than the lifetime of the universe. You are never going to have this complete. And it doesn't matter how fast a computer you try to get. It doesn't matter if you say, what if I got a whole bunch of computers and tried to divide the problem up, get all the computers in the world, run it for the lifetime of the Earth, and it still falls way short. So wouldn't be good. Okay, so we cannot use an exhaustive algorithm. We're going to have to do something faster. And for this problem, that means we're going to have to accept answers that are not, we can't prove they're perfect. In general, we can't find perfect solutions to this problem. We just try to find answers that are pretty good. Okay, so we're solving a variation of the traveling salesman problem. Who's heard of the traveling salesman problem? You guys all heard of it, right? So that's the classic traveling salesman. You have to connect, you have to pass through a bunch of points on the surface of the Earth, right? Go to a bunch of cities. So this one is related to that problem. It's got a couple of extra constraints, right? You have to start at a depot and end at the depot. You have to go through the deliveries in a legal order where you make all the connections, make all the deliveries. And it's in a street graph. So your time to go from one spot to another is itself found through a graph algorithm, right? By finding the shortest path between those 2 points. So it is traveling salesman, but with some extra, a few extra complexities to it. Okay, so traveling salesman by itself is already what's called a computationally hard problem. We've added in a few extra constraints and so on, and that doesn't change whether it's computationally hard or not. Still computationally hard. Okay, what does that mean? So for computationally hard problems, this means that if we have n deliveries, there's no guaranteed optimal solution. Okay, guaranteed optimal means we guarantee this is the best you can do. It's the lowest travel time anyone's ever going to find for this problem. We can't guarantee that in polynomial time. Okay, so polynomial time means we can take the problem size, which we can represent as n. That's really what the number of deliveries is setting our problem size here. And if there was a polynomial time algorithm, it means there would be some algorithm that is n to the k. We don't know what k is. Maybe it's 2, that would be squared. Maybe it's 3, that would be cubic. Maybe it's 100, n to the 100th. Computationally hard is worse than any of those things. It means that no matter what k you pick, n to the 1000th, the compute time grows faster than that with n. Okay, you cannot pick any k where the compute time is bounded by n to the k. So in practice, that means it's complexity of these computationally hard problems like this is at least exponential. Okay, so 2 to the n, or sometimes somewhat worse than 2 to the n. And that's a big number, right? That means that if I add one more delivery, the computation time you need doubles. Okay, so that's a big deal, because I could add another 100 deliveries, and every one of them was doubling your computation time to get an optimal solution, so you're not going to be able to keep up with the problem size. Okay, so for problems like this, you need to use heuristics to solve. Does anybody know what a heuristic means? What does heuristic mean? Actually, probably should have looked up a formal definition, but basically in computer, maybe I'll ask Professor Chong, maybe he has a good definition, but in computer engineering, computer science, it means it's like a good idea. Okay, so it's seems like a reasonable thing to try. I can't prove it's the best, probably isn't the best. In this case, we know it won't be the best, but it's a reasonable idea, and we can test it, and we can see if it usually works pretty well. So that's a heuristic in computation. Okay, so most research problems, you actually work on algorithms, are computationally hard. That's where people spend their time. If there's a perfect solution, people just use it, right? They have to be able to code it in their domain, but then they're kind of done. And these come up in all sorts of domains. So I've told you that I work on integrated circuit design. There's lots of computationally hard problems in that. Drug design, so trying to figure out how do you make certain shapes of molecules, how do proteins fold, that's computationally hard. Transportation network design, so how do you work out what's called operations research, like good transportation schedules and how to allocate my trucks and my planes and so on. So these computationally hard problems are kind of all over the place. They tend, when you solve them, you often use other algorithms that are perfect. In this case, we're going to use your M3 algorithm as one of our building blocks. But then there's some other portions that are computationally hard. So that's a pretty common thing when you're working on algorithms. And we have actually one of the pioneers of complexity theory, this notation about what is computational hardness, what is the difficulty of certain kinds of problems. Stephen Cook, who's a professor in computer science. So his life story is kind of interesting, so I'll share a couple things about it. So he came up with the notion of NP-complete problems. Okay, no polynomial time solution is known, or basically he worked in the area of NP-complete problems, and those are problems that are computationally hard. So there is no polynomial time solution, no n to the k solution, order n to the k solution for any k on conventional computers. He proved that if you ever find a method to solve any of these problems. Okay, so there are a whole bunch of them. I just talked about integrated circuit design, drug design, transportation networks, lots of other ones. If you ever find a method to solve one of them in polynomial time, that all of them can be solved in polynomial time, because with appropriate transformations, you can actually transform all these problems into each other. And so this is actually a pretty amazing proof, actually. It's a very surprising proof. So he was able to prove that if you ever find an algorithm like this, you can solve them all. And this turned into what is a very famous problem now in computer science, P versus NP. So P is the set of algorithms or problems that can be solved in polynomial time, and NP is the set of problems nobody knows how to solve them in polynomial time. But if anybody ever finds a way to solve any of these NP problems in polynomial time, they basically prove these two things are the same. They can now solve them all. No one has actually been able to prove that these NP problems cannot be solved in polynomial time. It's just no one's ever found an algorithm to do it, so we think probably it doesn't exist, okay? But nobody's proven that one cannot exist. So it is, if you want a high-risk graduate studies program, you could try to prove that P is either for sure not the same as NP or for sure the same. Because if you did, you'd solve an incredibly famous problem in computer science, and if you actually prove P is NP, you just solved all the computationally hard problems, you're gonna be super famous and probably do super well, but probably it can't be proven, right? So it is a very high-risk thing, because it may not exist. Anyway, Professor Cook's life story is kind of interesting, because in 1970, he was actually an assistant professor at UC Berkeley, and he was denied tenure. And you guys are before that phase of your career, but if you go into academia, you become an assistant professor, you work like crazy for 6 years. At the end of this is very different from almost any other job. At the end of 6 years, people around the world, experts in your field, evaluate you, and the department makes a decision. You're either given tenure, which is a job for life, or you're fired, okay? So it's very strange. Companies don't work this way. It's actually a very stressful way to live your life. For 6 years, you're kind of going, I don't know if I'm gonna make it or not, and then you either make it, and yeah, you're good for life, or nope, you're done. That 6 years didn't count, you're out. So he was denied tenure, which is actually kind of a crushing thing for a lot of people. In 1971, he published his most famous paper that basically showed that if you could solve any of these NP problems, that you could solve all of them. They basically would all be proven to be P problems, polynomial solvable. In 1982, he won the Turing Award, computer science's highest prize. So I believe it was right after 1970 they actually came to U of T. So he didn't get tenure at Berkeley, but he applied elsewhere. He came to U of T, published this very famous paper, won the Turing Award, and apparently sometime after that, Berkeley phoned him up to say, if you would like to come back, we'll give you tenure now. But he didn't go back, right? So this is actually, it's an interesting story in kind of resilience, because this actually would be quite a crushing blow. Obviously it didn't crush him. He went on to have a brilliant career. It's also held up as like an example of perhaps the worst tenure decision ever made by any computer engineering or computer science department. So this was not Berkeley is not happy probably that they made this decision in the long run. So there aren't that many Turing Award winners. Okay, anyway, so that's an aside on computationally hard problems. So you're not going to get a perfect solution. Actually, one of my grad students a couple of years ago just went, I think for at least moderate-sized problems, I could just try them all. So he did that. He left the program running for some of our smaller problems we use in Milestone 4 for 2 weeks. It didn't solve them. Okay, so he has also proven that even if you code it super cleverly, you're not going to solve this perfectly. Okay, so you're going to use heuristics. And they won't get the best answer, or they're certainly not guaranteed. They might get it by fluke, probably won't, but they run in a reasonable time, and you're trying to get just a reasonable answer, a good answer. Okay, so any ideas for a heuristic? A lot of heuristics just come about of this seems like a good idea. Some come about if you read a bunch of papers and you get ideas from others, but some heuristics just come up because you think, how would I attack this? What would I do as a human, and maybe I can code that up in a program. So I showed you the very first solution we could do, which is just take the delivery order we're given and just hook it up. Let's try to do a bit better than that. So what would be smarter than that, but still not too hard? And I think somebody must have an idea. If I gave you this problem with a whole bunch of deliveries, what would you do? Could you do better than my hypothetical Uber driver who just drove back and forth to the 401, right? Just went from top to bottom of the list. So I believe someone must have an idea, right? If I gave you a list of deliveries to make in a car, I think you would do better than just going down the list in order. Okay, so A09, do you have an idea? Go for it.
Well, I'd start with like the closest destination to my current.
So you're gonna try to sort them, kind of thing, right? So you're gonna go to the closest one. So yeah, that's the first heuristic I have too. So we're gonna find. I'm gonna look at all the depots, okay, and I'm gonna see from which depot what's the shortest distance I could use from a depot to a pickup. Okay, so what delivery is closest to some depot, and start at that depot and go to that pickup. And I'm going to go back to A09. Hopefully I captured what you were thinking.
Yeah, but actually I also had a question. If like one were to, for example, like prioritize where to go to based off like current position and the nearest nearest delivery position, would that result in the most optimal time or not necessarily?
So you're not getting optimal time for this problem. Like, it's computationally hard, you are not getting optimal, it's all heuristics, we're only gonna check how good is your solution.
Okay.
Okay? Does that make sense?
Yeah, but okay, but would that also like, so not necessarily like to answer my question, like is it not necessarily like if you were to just order the places you're going to go to based off like your current position and what's...
Yeah, so you can use distance to estimate travel time, right? So this is another good question. How do you figure out what's closest? Do you mean geographically closest or the closest in travel time? We're going to talk about you can do it either way. Easiest would be, let's just say, geographic distance, okay? Because that's easier to compute. So let's get that going first, but yeah, we can actually see how we can use the real travel time that's found by your milestone 3 to make this a little better still. Okay, so we're going to look at all our depots and look at all our pickups, find what depot is closest to some pickup, and that's the first thing we'll do. We'll pick the truck up there, we'll go to the closest pickup. Now what do we do? Okay, well, we picked something up, we could go drop it off. So I picked up some package P, I'm going to go to wherever it's supposed to be dropped off, and now I've got a decision to make. What do I do next? Okay, so same idea, well, I'll just go to whatever's closest, right? So I'll go to I know what pickups I haven't gotten yet, I'll go to whichever one of those is closest to where I am right now, and I'll just keep doing this as long as I have packages to deliver, and at the very end I got to go drop the truck off, and I got to go put it back wherever I got it from, so that's not really a decision. Okay, so it makes sense, it's not going to be too hard to code, and it is intuitive. Just go to the thing that's closest. So we should check, is this fast enough? Because we saw that trying all the orders was too slow. So if I want to go from any depot to the nearest pickup, well, the number of choices I have D depots, and I'm going to compute, let's just say I'm going to do it by geometric distance, right? But I need to check how far is it from every single pickup, so there are n of those. So this is going to be, D times n computation. I can do this with a couple of for loops. For all the depots and all the pickups, figure out what the distance is, pick the smallest one. This while loop, I'm going to go through n times, right? N pickups. And in each one of them, this is just order 1, but to find the nearest remaining pickup, well, I have to look through all of my pickups, which could be n of them. Okay, so that's an order n because I'm going to loop through all the pickups saying how far am I away from each of these, find the smallest one. Okay, so n times through a loop that is order n, so that's n squared. And then the final thing of just go to the starting depot, there's no real decision to make there, it's order 1. So if I add this all up, it's order d times n plus n squared, which is not that high. Okay, so my algorithm is n squared, and we're not going to give you really big n's, right? The biggest n we give you is maybe 100 or 200, so n squared's okay. It's not going to blow up on you. And it's hugely better than 2 to the n. Okay, so let's see if this is fast enough. So n squared is not bad. This n squared is what's going to dominate. I need to find from every depot, let's just take the first decision I have to make. From every depot, I need to know what's my travel time to every pickup. So here's my little sample problem with 4 deliveries to make in 3 depots. So let's start off here. For this depot, I check my travel time to 4 different pickups, and then I do the same thing for this depot, and I do the same thing for this depot. Okay, so 12 total travel times for this small problem that I want to get, and then I pick the smallest one, and that's going to decide, let's say this was the smallest travel time, so that makes my decision. Start at this depot, go to that pickup, okay, so I call find path, I get that travel path, and I've made my first decision. Okay, so is this fast enough? Well, if we wanted to get perfect travel times, not use geometric distance, then we'd have to call our find path algorithm, from this depot to this pickup, this pickup, this pickup, and so on. Okay, so we're actually going to call our find path algorithm a whole bunch of times. Okay, so our find path algorithm has had a pretty good implementation for milestone 3 would be about 0.1 seconds for a typical pair of intersections. If I multiply that by the number of depots and the number of pickups, and I say I got 100 pickups and 10 depots, this already is about 100 seconds, and we're going to give you problems that big or bigger. So this actually is going to be too slow, because I was just figuring out what my minimum travel time was, or what decision I should make here. And that one, order d times n computation is already, if I use my find path to make every decision in there, is already going to be too slow. Okay, so it's already too long. And I can plug this in for the whole complexity of this algorithm. I say 10 depots, 100 pickups and drop-offs, and my find path takes about 0.1 seconds. This would take about 1,100 seconds for one of our bigger problems. And we're going to give you about 50 seconds, right? That'll be the timeout that we give you on your program. So 1,100 seconds is too long. Okay, so we can't do that. We already had one idea though from ece297 of how can we do this faster. So calling find path is not going to work every time. What can we do that's faster than that? I kind of already mentioned it. So let's see, let's go to C06, I think.
Could you just use the geometric distance instead?
Sorry, let me turn off.
I was going to say, could you use the geometric distance instead of find path?
Yeah, so we can use geometric distance. Sorry. So yeah, we can use geometric distance instead, and it's not going to be perfectly accurate, but it'll be reasonable. And we don't have to get perfect solutions in this problem anyway. We already know it's not going to be perfect. So it'll just cost you a little bit of quality, but it's much faster. So if we estimate it as geometric distance, the time to compute, the distance between 2 points using your M1 function is going to be really fast, okay? So, on the order of maybe 100 nanoseconds, maybe even less than that on a fast computer. So if I multiply this same number of calls that I need to make to my how long does it take me to go between these 2 points by this much smaller number, okay, now it's going to take like a millisecond for you to make all these decisions. So with geometric distance, this algorithm is way faster than you need, okay? It's not going to be a problem at all, or at least the part where you're choosing delivery orders is going to be very fast. Now, we don't want just delivery orders. In the end, we actually want a travel route, including all the street segments between these. But if you figure out the delivery order just using geometric distance, and then you call find path just to make all the connections implied by that delivery order, well, there only are about 200 travel paths between those intersections. And if your find path takes 0.1 seconds, You can call it 200 times, it takes 20 seconds, that's less than 50, it's fine even for one of our bigger problems, okay? So it's gonna be fine. So this algorithm that we just came up with is going to be fast enough if we use geometric distance or some other fast way to estimate travel times. And we can call find path at the end to hook up the travel paths. Okay, so let's see what it would do. So if I actually ran this algorithm on this problem, this is my, from any depot to any pickup, this is the shortest travel time over here on the right. Okay, I'm now at this pickup, and I'm gonna say, okay, I gotta go to the drop off, so I'm gonna go over here. Okay, so I drop off a package. Now from there I say, what do I do next? So I'm gonna go to the closest pickup, which is here, and I'm gonna go drop that off. So I go all the way across the city to here, and then I go, what's my next closest pickup? And it's saying it's here. I pick that up, I go drop it off. Now what's my closest pickup? It's pretty close by. I drop that off, and then I gotta go back to my original depot, so I go there. This is better than my random solution. Still doesn't look fantastic, but it is better. Do you think, could you do better than this? Could you do better than this with like a small change? So as I was doing this, you might have gone, well, that doesn't seem like the smartest thing to do. So is there some change we could make to this heuristic that's not very complicated that would make it work better? And this already will get much better answers than just using the order we were given. So what do you think? Any ideas on how to make this a bit better? So let me show you like one where I kind of question what the algorithm's doing. So I'm here. I have so far picked up package A. I've dropped off package A. Now I've picked up package C, and I'm going to go drop off package C. And I go all the way across the city to do that. Is there anything I can do that seems a bit smarter than that? So let's go to E09. Whoops. Yeah, what can I do that's a bit smarter?
Instead of thinking like about the drop-off, like just when you have picked it up, can you like look from like the one you have picked up, like to other pickup locations?
Yeah, I could pick lots of stuff up. I got a big truck. So what would you do instead of going all the way over to C?
First, could you go to D?
Yeah, so I'm really close to this. Why don't I just go by there? Okay, so I'm going to show that in a minute, but yeah, that seems more logical. I'm kind of driving right by this all the way across the city. If I pick up B, I know I've got to do this eventually. Why don't I do it while I'm in the neighborhood? So, okay, so let's call that heuristic 1+++. So a bit better heuristic. The code's not much different. I start off the same way. From any depot, I find the closest pickup. I'm going to do that first. But now, while I've got packages to deliver, I'm going to go not to just the next pickup, I'm not going to just drop this package off. I'll go to the next, the closest legal thing I can do. And there's two things I could do. I might drop off a package, or I might pick up a new one. So I'm going to consider all those, and I'll do whatever's closest. And then I just add that into my path. And at the very end, I go back to my starting depot. If I work out the complexity of this, this loop now I go through this loop 2n times, and I have to check how far am I from n things every time I hit this statement, so I multiply that out as 2n squared. So if I add this up, it's a little more work, but it just changed the constant, right? My complexity is still the same. It's d times n plus n squared. So this algorithm does not take me a lot longer than the previous one. It will get better answers. Okay, so let's see how this one does. So I start off the same way. From any depot, what's the closest pickup? So this is where I'm going to start. I looked at all 3 depots. This is the one I like. But now I'm always evaluating, should I drop off something? So I could drop off package A, or should I pick something else up? And package D is closer to pick up, so I'll pick it up. By picking up package D, I'm also giving myself more options. I could drop off package D, drop off package A, or I could pick up something else. So the closest thing is drop off D, then I could pick up B, C, and now I can drop off the last things. And the travel route looks actually a lot better. So this small change gives a significantly better answer. So both these heuristics, 1 and 1+++, plus are what are called greedy algorithms. They make the next decision greedily. They do whatever seems best without changing any prior decision. They never go back and change a decision. So greedy algorithms are generally fast, which is good. They often don't get the best solution. They actually can sometimes. So